and start with that way, baby. Okay, so let me see what we have here. All right, the first question, guys, will be about a busways. So question number 1 will be about busways. Now, busways, I'm going over one question review. You guys will have 2. Did you guys hear me? On the test, there will be 2 of these. One will be 208 and the other one will be 480. Same calculation. I just want you to do the 2 voltages. So I'm only showing you an example of one because the rest is going to be the same. Okay. This is not the first time you guys have seen this. We've done bus dot before. I have a busway and I need to size it. The busway is 483 phase. 483 phase. And I need to size the following atom. First, number 1 is the copper, which is the actual busway. Number 2 is the overcurrent protection device for the busway. And number 3 is the feeder that feeds that busway. The feeder that feeds that busway. Cool. 3 things. The busway has a plug-ins. Can you guys see that? And in the plug-ins, there are 4 motors or 4 machines, 20 horsepower each. 3 machines, 250, 25. 5 machines, 30, and 6 machines, 150. And your job is to size that busway, the plug-in busway. Cool. All right, so let's go ahead, guys, and start. The first thing you need to do when we size that baby is you need to go to 430.250 under 480 and find the full load current, right? We're going to size it based on the full load current. So the full load current, guys, is will be 271. I believe this is 271 times 4. So 271 times 4. I can't see my. Can anybody verify that one? I can't read my handwriting even. Okay, or I think it's not 200. No, 27. Dutch. Yeah. That sound doesn't sound right. Okay, so 21 times 4. Yep, at 480. Can you guys verify that one? Should be 21. 27. Thank you. Oh, gosh, my handwriting. 27 times 4, right? What's the 27? That's the amp that you get from the NEC code book. What's the 4? There's 4 of them. Very easy. Then the second one, guys, will be 34 amps times 3. The fourth one would be 40 amps. These are all amps times 5. Now the last one, atom, I split it into 2. Anybody knows, guys, why I split the last 150 into 2? Yes, the largest one plus all the others. That big boy is the largest motor, so you need to increase one of them 25%. So you take 180 first and multiply it by 5. You take 5 of them and multiply it by 180, and the last one 180, and the last one, guys, 180. You multiply it by 1.25. Everybody knows why I split this one into 2? Because you take the largest motor, one of the largest motors, and increase it 25%. Not all the largest motors. One of them. I took one of them here, and the rest, which is 5 of them, are right here, right? Makes sense? And then you add them up, Adam. When you add them all up, you're going to find it's 1535 amps. 1535 amps. 1535 amps. 1535 amps. Cool. Now, please bring your DeWalt. I gave you also the sheet, Matt. I copied that sheet for you that you need to size based on. Then you're going to take, to size the busway, you're going to take the 1.535 amp, take it to DeWalt 3-13, or the sheet that I copied that sheet for you, Karen. So when you guys go there, you're going to go to the next standard, which is 1600 amp. And you go up. If it's not a standard, where do you go? If it's not a standard, gentlemen, you go up. You go up. Any comments, guys, about this? We've done this before. So, piece of cake. You're going to do the math, add them up. Move on. Yes, no? Okay. Next, you need to size the overcurrent protection device. The The overcurrent protection device is we take the same calculation 1, 5, 3, 5 amp. This time we take it to NEC 2011-240.6. You guys have this in front of you. And when you go there, we hit the jackpot, and we got ourselves the 1600 amp fuse or circuit breaker. 1600 amp fuse or circuit breaker. Feeder for the busway. That makes sense. And I know you guys, I gave you a copy of the stuff, so they expedite the process. Otherwise, it'll do a lot of writing. Okay, feeder for the busway. And Adam, I want to bring to your attention to the word match overcurrent protection device. Can you guys see that? Match overcurrent protection device. So I need to, my overcurrent protection device, guys, is 1600. I want to divide it by 4. Why 4? Remember when 1600 is a big, you can't find a conductor that carries 1600 amp. So you need to parallel. Why did I divide by 4? Because that'll give you 400 amp, and that 400 amp is a good place to parallel. So that'll give you 400 amp, right? So 4 sets. If you take the 400 amp to 310.15 B16 75 degree column, gentlemen, you're going to have 4 sets. 4 sets. Each set is going to be 3 conductors, 600 kcm THHN, or we assume a dry location and we're assuming it's THHN. Now for the neutral, 90% of the time, Karen, the neutral will not exist. When you guys have three-phase machines, here's a machine like this. Three-phase machine, the last thing I'm going to do is bring a neutral. Why do I need a neutral? For this one, we have 3 phases because we don't want a neutral. So 90% of the time, that busway will have no neutral. No neutral, just 3 wires going to it. If there is a neutral, and you want to size it, which is, I said, probably 10% of the time, then this is how one way of doing it. You take the 1600, so I'm going to take you guys to the 1600 amp, take this one, and take the first 200 amp, remember, leave them alone. Anything higher than 1600 minus 200, multiply this by 0.7, and add them up. So that will give you 1180 amps. That's the neutral amps derated. Anything higher than 200 amp, remember you add them up here. Then you take 1180, parallel them by 4. That's step, and that will get you 295 amps. And if you take it to the same table, guys, table 310.15 B16 under 75 degree column. And gentlemen, you should get, ladies, you should get the following. You should get 4 sets of 1 conductor. Each one of them is 350 kcm. Again, this is one way of sizing the neutral. If they actually, based on the loads that I'm telling you guys, based on the loads that I'm telling you right here, the neutral should be 0. There is no neutral. If you were to size a neutral, this is one way of doing it. Again, I can't emphasize, this is 10% of the time. Cool? I don't want you to hang up on the neutral. Typically, there are no neutral with these busways. The beauty of the 3-phase system is get rid of the neutral for 3-phase loads. Cool? Everybody's good? Move on? Yes, no? Okay. Then we need the equipment running conductor, guys. This baby here, it's called the equipment running conductor. The equipment running conductor, if you go to 250.122 based on 600 amps, we size it based on overconduction device. You're going to have 4 sets of 1 conductor. Each one of them is 4 AWG, THH, and bare or cover. Bare or cover. Okay, so then when you put your conduits, gentlemen, you're going to end up with 600 kcm for the phases. For the neutral, you're going to end up with 250, and for the ground, you're going to end up with 4 odd. So Adam, if I ask you to go size the conduit, How many conductors you need, Chad? I have 603 conductors, 600 kcm THHN, one conductor, 250 kcm THHN, and one 4-aught ground at THHN. Easily, you do the calculation and you size your conduit. So you're going to see 4 conduits like this. And you guys have a graphic of this, right? Any comments, guys? Any questions? Now,
For your neutral, you got 295. You got 250.
let me see. When I did the neutral, 295, yep. 350. Did they say 250? Have I lost that? Oh, 350. Sorry. This is 350. Oh, I was just missing a leg here. A leg for the 3. Any comments, guys? Any questions? Now, remind you guys, you're going to have how many of these? 2 tomorrow. One will be 208 and one will be 480. Same calculation. Okay. Next question, gentlemen. We're going to have a load and size a generator for this baby. And also, can you write yourself, you're going to also have 2 of this, please. You're going to have two generators. Same thing, guys, same sizing. So I just want you to practice a little bit more. So we're going to have, so we're done with the busway. We size the busway. We're going to have 2 examples about the busway, 128, 1480 tomorrow. Same calculation, different numbers. For generators, here's a gen that I tie to my system. The load that I need to pick up, guys, is 431 kVA. Please pay attention to the word kVA or kW. Please pay attention if it's kVA or kW. If it's kW, you have to divide it by 0.8, right? That's power factor. If it's kW, and then size. So did you guys hear me tomorrow, Derek? You're going to have one of them in kW. So what do you need to do? You take the kW, this number, and divide it by 0.8. That will give you the kVA. Then you continue with these steps. This one, why? Because look at what I'm giving it to you in what? In kVA. If you have the kVA, you don't worry. You don't need the power factor. Okay. So, I need to size the gen size first. Then I need to size the overcurrent protection device. Then I need to size number 2. Number 3 is the feeder. Number 4, I need to size the grounding electrode conductor. Number 5 is the main bonding jumper. This here is called main bonding jumper. This is separate directed. Cool. I'm going to size all these 5 things for this generator. 5 things for this generator. Cool. Do you guys remember that sheet that I gave you from the wall? Have that sheet handy. And if you guys go to 3.13, I copied that sheet. There's a sheet that I gave you guys. It's not going to have it on yours. I give you a sheet. If you don't have it, I can make you another copy of it. You need this one for the sizes, 100%, because you don't have the generator sizes. I just wrote in there. Where did it go, Chad? I don't have it. I can make you a copy if you don't have it. But what you need is a copy of this sheet, guys. That sheet, if you don't have it, I'll make you a copy of it. If you go there, under generators, I pulled these from Cummins, I believe. So since it's 4, you're going to take the 431 kVA and 3-13, where I put these for you guys, and you're going to end up with 438 kVA. 438 kVA. You go to next standard. So, Matt, in a real life, you guys have a generator sizing software that we're going to come up with, right? You're going to get this number, that particular number from where? From the generator, the software, common software that we have. You're going to get that number from there. Did you guys hear me? When you're doing your project, that number that you, instead of going to the DeWalt and guessing about it, you're going to find this number right here. This is going to be coming from the comments. After that, gentlemen, we need to do the following. So we have our generator. Then we need to find the overcurrent protection device for this generator, overcurrent protection device. Then you take the 438K, the size of the gen, divided by 480 because the voltage, the voltage is 480, multiplied by 1.73, and that will get you at a healthy 527 amps. That's the full load amp of this gen. Then you take 1.25, and I use 1.25, I used to use 1.15, guys, because that's the conductor from the overcurrent protection device right here into the generator. So that conductor, when you size it, assume it's continuous load, and you take 1.25, multiply it by 527, you're going to end up with a healthy 659 amps. 659 amps. Take this one to 240.6 atom, and you get yourself a healthy 700 amp circuit breaker. You go up if it's not a standard. So you have 700 amp circuit breaker. 700 amp circuit breaker. Like I said, I used to multiply by 1.15, but when you're sizing the feeder, guys, from here all the way to the terminal, that conductor here, assuming it's continuous load, worst scenario, and that will get you a 700 amp. Okay, so I know what size overcurrent protection device do I have. Everybody's good? Good? Okay. Then I need to go generator feeder size. I always say match overcurrent protection device, guys. Since we have a generator feeder, and we need to find match overcurrent protection device, right? So I have 700 here, 700 amp. And it's not a good idea to carry a 700 amp feeder, right? Remember, if you go higher than 400, what do? Cut by start with 2 and parallel. Start parallel. So this is easy. Let's parallel 2, right? Not 3. When you parallel 2, guys, get you 350 amp. 310.15 P16, 75-degree column, get you 2 sets of how many conductors? 3 conductors. Each one of them is 500 kcm. 500 kcm. 500 kcm. Now, generator, you need a neutral. Why do you guys think that a generator need a neutral? Because when you have a generator, you might have Atom 277 lighting fixture here. How are you going to burn a 277 lighting fixtures unless you have a neutral on a 480? You have to have a neutral. So for the generator, these are the phases. The neutral, my friend, is I would use the same thing, 700 amp. Do this derating, the first 200, remember, leave it alone. Anything 700 minus 200, multiply them by 0.7, that magic, add them up. And if you guys come up with 550 amp, and if you take a 550 amp divided by 2, I have to divide by 2 here because I'm higher than 400, and also because I already parallel the phases. They'll give me 275 amp. Same table, same column in the table. Get you 2 sets, has to be 2 sets, of 1 conductor for the neutral. And it's 300 kcm THHN. 300 kcm THHN. kcm THHN. Any comments, guys? Any questions? Questions? Any comments? Okay, so that's my size. Good. Grounding electrode conductor. Grounding electrode conductor, guys. Remember, that's the one that take the neutral to the ground, bond the neutral to the ground. Grounding electrode conductor. When we size this one, if you guys remember, we take 2, we multiply it by 500. Anybody knows why we take 500 kcm? That's because we parallel. That will give you a healthy 1000 kcm. Then you take your 1000 kcm to 250.66. Add them, my friend, and you got yourself a healthy 1 aught AWG THHN bare or insulated. You don't have to have insulated. You can have it bare or covered. Okay, so that's the ground electrical conductor. It's a wire that you take it from the ground bar in the switch gear. And do you guys remember when we went to Boston Scientific and they showed that ground bar in the electrical room and all these wires tied to it? That's one of them. System bonding jumper. System bonding jumper. This is called system bonding jumper. System bonding jumper, Kieran, is the one that takes the neutral and bond it to the ground. It's a wire. You take a piece of wire. Here's the ground bar. Here's the neutral bar. You tie him with a wire. Okay? If it was a wire, then the same calculation does applies. The same calculation applies to this one. So we have the neutral system bonding jumper. You take 2, multiply by 500 kcm. That gets you 1000 kcm. You take your 1000 kcm, 250.66, table 250.66, table 250.66, and that will get you a healthy same number, 1, 2 aught AWG, 1 conductor THHN. I want to remind you guys for the system bonding jumper, if you looked at when we went over the exercise, if this number Aaron here that you came up with, please remember this for tomorrow. If this number is more than 1100 kcm copper, more, then you have to start multiplying this number by 12.5%. That's if you look at the exercise that we did. For the main bonding jumper, guys, you go to the table as long as you don't exceed 1100 kcm copper or 1750 aluminum. If you exceed that, then it triggers another requirement that you have to use 12.5%. And you guys did the exercise for me. So mine here did not trigger. Tomorrow, yours could trigger this. So so I always like to, so we got that one. I like to write a note for myself here. If 1000 kcm is more than 1100 kcm, then, obviously it's not, then you take the 1000 kcm and multiply this one by 12.5%. Obviously this is not true, right? This is not true. Write yourself that note. If the number that you came up with more than 1100 kcm, is it? No, so it doesn't trigger this. Okay, so for generators, how many examples do you have? How many on the test, guys? 2. The last thing that I have on my agenda is a transformer. Everybody's good? The last thing is going to be a transformer. Here's the transformer that we have, Karen. The transformers, you have only how many? 1. So for transformers, we only have 1. One question on the test. If you're upset, math, because we have 1 transformer, add yourself another one. Right? When you guys were in school, did the teachers ever ask you to write a question and solve it and they give you credit for it? Have they ever done that? Write any question in math. Our math teacher used to say every test that we have, he used to have 5 points out of 100 for your own. Write a question and solve it. And we used to be confused. Well, how am I going to write a question here? And some of us tried to make a question so complicated, so he started laughing at us. He said, write a question that you can solve. So, I don't know. Have you had this experience, Derek?
Yeah.
Write a question and solve it? Yeah. That was high school. Write a question and solve it. That was, yeah, that was in high school for me. We were doing calc in high school.
Yeah.
Primary feeder. Primary feeder, my friend. Okay, so let's talk about this first. I have a big, fat, fluffy three-phase transformer. If you're in Minnesota in the winter, it has to be fluffy because of the snow. The size of this fluffy transformer is 500 kVA. The primary is 4,160. Can you guys read my scribble here? 4,160 volt. The impedance, Z, is the impedance, is 5%. On the secondary side, Adam, we have 48277. And I need to size the fuses and the conductors on both the primary and the secondary. We did an example like this, right? You guys remember doing that? We did even more. What I'm asking you to do is just these 5 things. Find these 5 things. I don't want to find the line-to-line voltage and what's not. Okay. Primary. Let's do the primary feeder. The primary feeder, sizing the primary feeder, guys. You need to take I primary, take the 500 kVA divided by what's the voltage on the primary? 4160. Still 3-phase, 1.73. And if you guys do the math on this one, you get 694. 694 amp. Okay. Then we're going to assume it's continuous load. 1.25, assume it's continuous load, and I'm going to take 694, assuming it's continuous load, and that will give me 86868 amps. Then, Adam, we're going to take our 868 amps. Now, can I take this one to 310.15P16? No. Look at the voltage. The voltage is 4160. Up to 600 volt, 310.15P16 is good. Higher than 600 volt, you have to go to a different table. And I know you guys know that, but we went to table 3. This is the table that went to table 310.15. 310.60, 310.60C, and 77. And you go to under medium voltage dash 90 degree. You go to 310.60 C77. We have been there. You guys, when you did your homework for Chad, you went there. So highlight that table, go there under medium voltage dash 90. There's a 90 column. When you go there, guys, the voltage is 4160. So make sure you go into the 5K column, not the 15K column. There's 2 columns. If you go there, Adam, you're going to find yourself a healthy 3 conductors. Each one of them is 4 AWG insulation, medium voltage dash 90 degrees Celsius. That's what the name. Instead of THHN, MAT, that we use for low voltage, they use MV as stand for medium voltage 90. The insulation is rated for 90. The most common. There's MV 105. If you guys go there, typically you size based on 1 MV-90. That's it. That's probably the most confusing part of in the high voltage. Everybody's good? Now moving into the secondary feeder. Secondary feeder, Adam, is 480, so it's a baby one. So when you go there, you're going to take the same 500 KCM. Oh, not KCM. Did they put KCM? I hope I didn't do KCM. KVA. Did I do KCM here? That's the fluffing. Should I? No? Okay. 5 kVA. Divide this baby by 1.73 times 480, because that's the secondary side. And that will give me a healthy 601 amps. Now assume it's continuous load, 1.25, multiply this 601. Again, assume it's continuous load, and 751 amp. So then you have a 751 amp divided by 2, so we can parallel. So that will give me 375 amp. Take this one to 310.15 B16, 75 degree column. Why? Because the voltage is 600 volt or less. So I go to the regular table. Gentlemen, you get yourself a 2 sets of 3 conductors, 500 kcm THHN. Karen, if you say 3 conductors or 500 kcm and you stop, that's meaningless. You have to indicate the insulation. THHN. That's why I threw all these one for you tomorrow, guys. I would like you to write exactly like I do. How many sets, how many conductors, what size, and what's the insulation? Now you give me a full picture. Because how am I going to size the conduit? If you don't tell me how many of them, and what size, and what's the insulation, how am I going to size the conduit? You guys are electrician in the field, will depend on you to size the conduit for them on the feeders.
What table was that one on?
310.60C77.
Yeah, and under 90-degree column.
You go 90-degree column and 5K. Remember the one that says there's up to 5K, there's one set of columns, and then 15K another set of columns. Make sense? No? This is 77.
Yeah.
Okay. So 90 is up to 500. We're going to be right here. So what's the amp that we are looking for?
868.
No, we divided by 2, didn't we? Oh, 868. Oh, yeah, I'm in parallel. I just went directly. 868. Okay. Oh, I must. Interesting.
Because I can see it like you can parallel on the video. That was why I was like, I don't like that.
I'm so sorry, man. There's a dot in between here. Thank you. There's a dot. My apologies. That's what I thought. That's a high. Thank you. Thank you for taking that one. This is 69.4. Can you guys put the point right here? Thank you. That's where the confusion happened. That's what I thought. And this is a point. We're just missing a decimal. Not a big deal, but you're just missing a decimal. Okay, this is 68.8. Does it make sense now? 68.8. And this is a decimal here. That makes a lot of sense. I apologize. That's a lot of amps, though. 694 at this level.
500,000 divided by 4160.
And then divide it again by, I don't know how you calculate, or you have to put brackets or divide it by 1.73. Okay? My apology. Thank you for picking up this, because it doesn't make 86.8. That makes a lot of sense now. Okay.
Wait, so then it was
Then you go higher.
86, so okay.
You go to next standard.
I got it.
Good. Thank you. One of us is aware. Neutral size. For the neutral size, guys, we take the 751 amp. Remember the whole magic deal here, 200 amp, leave him alone. Then 751 minus 200. Multiply this by 0.7. Add him up by 0.7. 0.7. And when you do this math, guys, that we have done this, you will end up with 585 amps. And then add up, you take the 585 amps, you have to cut them by 2 again, because we parallel. So that will give you 293 amps. And don't forget to take this one to table 310.15B16, 75-degree column. And that will give you two sets of one conductor for the neutral. It's a 350 kcm THHN. Gentlemen, that's it. And ladies and gentlemen. Any comments, guys? Any questions? Adam, please do not forget the neutral sizing. When you size it, always think of the neutral. If there's no neutral, no neutral, you know. But The worst scenario is if there is a neutral. Cool? Oh, we haven't figured that one yet. So the primary overcome protection device. Now let's go to the primary overcome protection device. So that's a neutral. The primary overcome protection device, guys, on the primary side, you go to table 450.3a, you take 3, because it tells you so, multiply it by 69.4, and that will give you 208 amps. Then you take your 208 amps to 240.6. That'll get you 225 amp, and you are allowed to go up. You are allowed to go up from the table because it has not number 3 there. On the secondary side, Adam, your multiplier is 1.25 multiplied by 601. That will give me a healthy 800 amp. You take your 800 amp, 240.6, and that will get you, secondary, that will get you actually different. I'm looking at, get you 751 amps. Take the 751 amps, that will get you an 800 amp. 800 amp. And the last two, these are your overcome protection device fuses. Then the short circuit guys are a piece of cake. On the secondary side, you take the 601, always the secondary, divided by 0.05, and that will get you a healthy 12,000 amp. Don't forget the 12K, 12,000 amp. If it's not a standard here, Adam, we went again up. Can you guys see that? If it's not a standard, you go up. Why do you go up? Because if you guys go to table 450.3a, it will tell you on the primary and the secondary in this scenario, if you don't hit a fuse, do not get mad at Chad, just go up. Cool? Comments, questions? I know I went fast through them, guys. This is a review. We have done this before. Hopefully it's the second time. We'll test you on them. Okay, shall we have 5 minutes until I download and then I'll go over the theory? Everybody's good? Okay, thank you. This will be PDF'd on the network too.
You just said it was 3%?
5%. Was it 3?
No,
Let's go back directly. See, there's the impedance is right here.
all right there.
The impedance 5%. Yeah, that's all right. And you just divide the full load current on the secondary side by the impedance. All right.